So, in this talk, I'll be speaking about a few historical evolution and arguments and counter arguments between two parties. Uh, One party was the bandwagon of Einstein, which were famously known as the uh, EPR band, and on the other hand, Schrodinger. So they Einstein, along with his team, came up with this thought experiment of having a pair of particles which are separated away from each other, and their claim was that whatever physical quantity that we are interested in measuring is predetermined. It's fixed. Whether or not we are measuring it or not, it's already determined. There is some definite value of that physical quantity, be it position, momentum, other physical quantity like orbital angular momentum, spin angular momentum. But mostly to understand what the issues were and how the paradox was resolved and all those things. And today we are at the verge of, at the brink of, we are actually using uh, this concept which used to be a paradox. That's why I used this word called praxis. Uh, because praxis, this word is more appropriate than using the word practice. I was initially thinking about from paradox to practice, but praxis is in a more philosophical way, which is like uh, theoretical development and practical application go hand in hand and contribute to each other. That's what praxis means. Okay. So, so debate goes back to 1930s, where Einstein, Podolsky, and Rosen uh, claimed that at some location, if there is some particle, pair of particles which get separated, and and here is particle A, signifying that Alice, one of the user receiver who receives it. On the other hand, Bob receives another particle, and Einstein claimed that if I, from the principle of conservation of momentum and the fact that the center of mass doesn't move, given the values of XA and PA, I mean the momentum and position of the particle that Alice received, I can just deterministically know the value XB and XB and PB received by Bob. So, so that means there was already decided or predetermined variable which defined the physical entity of the particle that Bob received. Okay, so in a way, XB is the element of reality. If we are talking in terms of position, and if we choose to talk in terms of momentum, then PB is the element of reality. In a way, these are the so-called hidden variable, local hidden variable that would predetermine the 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 reality of the of that distant particle, which is with Bob. But on the other hand, the quantum mechanics that was developed by Schrodinger, which came up with this uncertainty principle, there would be an uncertainty in measurement of uh, the position and momentum of any particle which is located in any place. So, in a way, quantum mechanics is not able to exactly pinpoint what the position and momentum of particle B is. So in that sense, quantum mechanics is incomplete. It could not give the complete information about the other particle. So that's where the paradox lies. I mean, so that so simple. Einstein, along with his team, demonstrated that knowledge of uh, predetermined values, they can know all the information about that distant particle. Okay, so so that's where the paradox was. Quantum mechanics was disturbed quantum steering. He said that in a way, particle A, I mean, with Alice, we would somehow, on the basis of her measurement, will steer the particle with B, with Bob. And he also, in an attempt to, justify or attempt to resolve this question raised by Einstein, he he also came up with this idea of definite hidden state that must be assigned to the particle uh, with Bob. Okay, so they were like, but he was himself not sure whether this steering and this hidden state that distant particle. We are talking from the point of view of Alice. The particle with Bob has a hidden state, local state, quantum state, which defines it, something like that. Okay, so this debate went on quite a lot until, as all of us know, that Bell actually resolved this issue, that he structured a mathematical framework which very non-local interaction. So Einstein's another uh, criticism about quantum mechanics was that somehow you are saying it can steer a distant particle. So how will that information pass to the distant particle? It will violate the causality principle. The information seems to be passing with a speed more than that of light. So these things were to be resolved. So with Bell's inequality, it was clear and resolved that, okay, we have to respect causality. We have to respect that nothing passes, faster than light, travels faster than light. But we have to come to this understanding, or we have to accept, and which was experimentally proved, of course, in due course of time, that um, the assumption that the things were predetermined before whether or not you are looking at it or measuring it, that has to be abandoned. So, which is called realism. I mean, realism means something which already exists, independent of your measurement. That is realism. Realistically, it is there. So that's not the case in quantum mechanics. And the fact that you are saying local effect exists, so quantum mechanics also violates locality. Non-locality is a fact, is a scientific fact which was uh, proven experimentally, because of which Nobel Prizes were awarded to three scientists in 2022 because of their groundbreaking experiments. And it started with Bell's uh, experiments, thought experiments. And what I will do is to if so Bell's inequality is basically we will think about some scenario in which two particles get separated, and two people who receive those particles will perform experiments on those particles, and their results, the outcomes, will have some kind of an upper limit. Okay, some kind of an upper limit. It should not exceed that value. And if at all, locality, realism, these two principles which have to be abandoned, because pre-quantum era classical mechanics, Einstein was a champion of classical mechanics, developed GT, general theory of relativity, and all those things. So locality, realism have to be abandoned. And if accepting localism and locality and realism, we determine the outcomes of the experiments, and we see that it cannot go beyond a certain value. So I will try to explain three scenarios, because Bell's inequalities cannot be just one master universal equation. You can come up with many such experiments which involve more than one particle separated away and somehow have some mysterious non-local connection between them. And if we do not accept that mysterious non-local connection, we stay in our classical era of localism and reality, the measurement outcome will not exceed that value. If it exceeds, then it definitely proves that we have to abandon local realism. We have to accept that non-locality exists, and the the state of a quantum mechanical system is fuzzy, is in the superposition of many findable states, combination of all those states. It's in a superposition of all those states, unless we make a measurement. Okay. So this is setup one, first setup. We'll try to go through them quickly. So these are about a kind of a pair of particles whose wave function is a combined wave function, composite wave function, and so this term called entanglement comes into picture. A single wave function actually describes both the particles, and somehow that wave function, if it cannot be factored out, cannot be written as a product of two separate wave functions, that essentially mathematically says that they are entangled. They are somehow entangled, they cannot be separated out. Okay. But we are not talking about those wave functions, we'll just simply go through experiments. Okay. So there is this source which prepares a pair of particles. One particle goes this way, another particle goes this way to Alice and Bob. And Alice has a choice of, measuring some observable A0 and A1. Similarly, Bob also has got two choices of measuring B0 and B1. They can be spin angular momentum along some axis 0 and some axis 1. Similarly, here Bob also has the freedom of making a measurement along axis 0, axis 1. So they make measurements. Okay. They make measurements. So this kind of an experiment can be repeated innumerable number of times. Okay. First particle comes, gets separated. Alice, let's say, measures A0. Bob measures B0. End of one experiment, another particle. Alice makes a measurement of A0 or A1, whatever, and this goes on. Okay. And the value of this measurement has a binary outcome, +1 or -1. This kind of a game, thought experiment. Okay. So if smartly you consider this term A naught B naught plus A naught B1 plus A1 B naught minus A1 B1. This is actually uh, can be written as this. So if we look at this term, A naught plus A1 whole into B naught plus A naught minus A1 whole into B1. Because A naught and A1 and these values are predetermined. They're predetermined. Like one particle got created, pair of particles got separated. They have already predetermined value. This particle had a value.
Voice is breaking. Your voice is breaking.
So in one experiment, you will get plus one. Hello, can I?
Your voice
Now?
is breaking. Yeah. Maybe you can switch off your video and then we may see some
Okay.
improvement.
Okay, just give me a couple of seconds. Yeah. Okay. I hope I'm audible now.
Yes.
Yeah,
Could you make? Yes.
Okay, let's see. So looking at this term, if we see either of this term, either this will become one. Sorry, so if A0 plus A1, on one case A0, A0 plus A1 will either be 2 or minus 2. Okay. So A0 plus A1, if this is 2, this will become 0. Okay. So that's the catch here. Either this will become 2, this at the same time this will become 0, or this will become 2, this will become 0, or this will be minus 2, this will be 0. Okay. So overall, if we keep repeating this experiment, the average value, the same function, the expectation value of these operators together will never go beyond 2, the absolute value of the uh, expectation values of these operators. Okay. But in quantum mechanics, locality and realism have to be abandoned. We know that the system stays in a superposition of these two possible binary values. I mean, binary states which will give you that binary value, +1 or -1. So, and the probability of finding along any axis will depend on the cosine of the angle. Okay. For example, if the state is in along this direction, the angular momentum is this direction. So the probability of finding the angular momentum to be +1 along this direction will be given by the half of the cosine of this angle. The probability is actually proportional to the square of the cosine of half the angle between these two axes. Okay, this comes from the if you most of us are familiar with the two-dimensional Hilbert space, and we know the geometry. Okay, so and if we smartly choose those operators A0 and A1 to be the spin angular momentum operators, famously known as the Pauli matrices. So sigma z and sigma x Here B naught and B1 are smartly chosen to be linear combination of these two operators. Okay, basically measuring along we'll see these expectations values will be 1 by root 2, all of them. Okay. And if we take the sum of all these operators, there will be 4 times 1 by root 2, which is 2 root 2, which is greater than 2. So this is where the it violates this inequality. So this is another this is a quantifier. This is a quantifiable yardstick of measuring non-locality. Okay. Similarly, second setup. Second setup is all are related to this, particle spin and momentum of particles. Okay. Now again, we have another setup is I have 3 axes: axis A, axis B, axis C, which have axis A, axis B, axis C. All are like, the catch is they have to be non-orthogonal. Okay, 120 degree each. Okay. So here you have Alice, here you have Bob. Alice also start, and after particle, pair of particle move to Bob and Alice. Alice starts measuring, and she has a choice of measuring along either of these axes, A, B, C. Similarly, Bob has the same freedom. So in this case, how many situations will be there? Keeping the, from the single source which disintegrates into 2 particles, conserving the spin angular momentum. If along axis A, Alice measures +1, Bob will measure -1. This has to be kept in mind. Axis A, axis B, axis C. Similarly, axis A, axis B, axis C. If at all, the particle would have, Alice would have chosen to measure the spin of particle along B, and let's say had gotten +1, then Bob would have gotten -1. Similarly, if this is +1, this is -1. So keep on doing this. We will have 8 such combinations, isn't it? So this place can be filled up with either 0 or 1. Sorry, +1 or -1. This is +1, -1, +1, -1. So 2 to the power 3. So 8 combinations. Accordingly, if this is +1, this has to be -1, and so on along a fixed axis. So there will be 8 such scenarios, 8 such cases, which means you will have 8 such different populations. Have number of such experiments you are doing, and out of n number of particles, you have n1 number of particles in which, if Alice makes the measurements along A, gets +1, Bob would have a spin -1 along A. It's totally classical and just conservation of angular momentum. And classically, these many varieties of particles will be there in an ensemble. Okay. So again, we'll make a situation. We'll ask the question: if here instead of Alice and Bob, we have named them Lucas and Rihanna. Okay, I hope you can keep track of it. So 8 such combinations. Okay. And if we ask the question, okay, if Lucas makes a measurement along A and gets a +1, and Rihanna makes a measurement along some other axis like B, how many situations will be there? What is the probability that they measure along different axes and get the same value of spin? For example, consider the set 2. Consider set 2. Lucas has measured +1 along A, okay, and Rihanna has measured along C, another axis, and got a plus. So this is one case. So how many such experiments? Experiments can be done? 9 such experiments can be done. Okay, here 3, here 3. 3 into 3, 9. Out of that, 4 favorable cases will be there where both of them have chosen to measure along different axes and got the same spin. That is what we are interested in. So 4 by 9. So it will be seen that some of the other settings, it will be even less than 4. So, for example, in set 1, it is actually 0, no such cases. In set 8 also there is 0, no such cases. And in other sets, it will be less than 4 by 9. So 4 by 9 is the maximum probability that they will get a same spin angular momentum if they choose to measure along different axes. Non-orthogonal axis, that is also another catch, because orthogonal axis, again, no special thing happen which will make us think that okay, something fishy is going on, and non-locality comes into picture. So non-orthogonal axis has to be kept in mind. Again, if we follow quantum mechanics, we know that the probability of getting a spin along different axes is governed by the geometry in Hilbert space. Okay. So we'll see if Lucas has gotten up spin or +1 along some axis A. Okay. Then the probability of getting a same spin along another axis will be given by the cosine, half of the cosine of the angle, and uska square, right? So 3 by 4. Similarly, another situation where, let's say, Lucas has gotten a -1. What is the probability of getting a -1 for Rihanna if she makes a measurement along some other non-orthogonal axis? You will get a 1 by 4. Okay. Now the choice of Lucas getting an up or down is because it's a uniform ensemble is 1 by 2. Okay, 1 by 2 and 1 by 2. So it's like combined probability. So the total probability of getting the same question. I mean, we are answering the same question. Lucas and Rihanna choose to measure along different axes, getting the same speed. The probability will be, first case, Lucas up is 1 by 2 into 3 by 4 plus downspin 1 by 2 into 1 by 4. So that will be 3 by 8 plus 1 by 8, which will be 4 by 8, which is 1 by 2. Okay. Which is more than 4 by 9. Okay. So again, following the classical, so this is like all the possibilities that an ensemble can have, these kind of possibilities. So this is in a way the prediction of classical mechanics, which is to say the values are predetermined, they already exist, and for some set of populations, they happen to have these values, some set of populations they happen to have this value, and so on. Okay, So here also it is, so this is also another violation where it establishes that quantum mechanics is true. Non-locality, I mean, locality and realism have to be abandoned. Similarly, another setting, I will not go into it. It is another kind of a setting, again, where it will be violated. Now, coming to some realistic situation. Realistic situation. What, you know, as of now, we were talking about, some composite quantum state psi, which contains the combined, it's a combined state which contains the quantum information of both the particles in a single wave function, even if they are separated. So these are kind of, pure states. These are pure states. But when particles will travel, they will interact with the environment, and the system will no longer be pure. So the systems which are not pure states have to be represented in a different way, for which we use the density matrix, which is like a statistical, uh, it's a kind of a combination of many quantum states, probabilistic distribution of many quantum states. Okay. So we need to also quantify, because experimentally we'll deal with such mixed states, and there also we have to deal with those kind of states. We'll know, and preparing pure states and sending them to far distance is near to impossible. So mixed states have to be also tried and tested in some way, in some quantifiable way, so that we can characterize them. We can characterize those mixed states and declare them eligible for our, quantum communication process. Because, if all this sending business is used in quantum communication or quantum key distribution. Same, I mean, uh, quantum key distribution uses measuring along measuring spin angular momentum along different axes only. I mean, the things which we discussed. So we have to talk about mixed states. That's why quantum entanglement, that which we talked about now, somehow the two particles are entangled, irrespective of whichever axis we are measuring their spin angular momentum. The entanglement is intact. This is a nice diagram, I would say. For all those pure states which we were talking about, the test is this quantum entanglement. I mean, if Bell inequality is violated, then they are appropriate for us to use them in our communication purpose. But there will be some mixed states. Mixed states means we are going towards classical regime. Okay, totally mixed or totally totally stochastic mixture of some particles is like total classical. Okay. So so quantum may not be able to filter out some of the actually legitimate mixed states which we could have used for secure communication. But Bell inequality may not be violated by those states, and we will be mistaken to say that, oh, they are not legitimate, they are not appropriate for communication. So that's why another set of testing, which we can say is more rigorous, and so-called mixed states will have to violate this boundary in order to be eligible to be called appropriate for technology, for communication. Okay. Similarly, there is another even stricter bound given by Bell non. We call this Bell non-locality. People may get confused by saying, okay, all this while we were talking about Bell inequality. So what is Bell non-locality? It's just a term. This the test is this Bell non-locality. If all these experiments, measurements, particles separated, and we are measuring them, we can describe those results, measurement results, by a total, classical, local hidden variable, probabilistic distribution of local hidden variables. Some model which gives you a probabilistic description of this measurement. If we can somehow reproduce or can explain the results by local hidden variables, then it is not secure. It is not. There is no quantumness in that. Okay. So we have some mathematical inequality. It has to be a local hidden. That means there is some quantumness. An upper step is EPR steering, in which we are saying one of the particle has got some local quantum state. And here, this guy, let's say Alice is making some prediction, some estimation of the measurement results of Bob. And you have a mathematical expression which gives you a probabilistic description which involves some local hidden state. Okay, so that is called local hidden state model. Bell non-locality deals with local hidden variable. Then a little above, EPR steering, which we call, is local hidden state and also plus local hidden variable. This kind of a modeling. If you can explain a result, result of all the measurements by a local hidden variable and a local hidden state kind of a model, if you can explain the result in this model, then okay, whatever system you considered, it is not eligible for communication purpose. And above that, this is completely pure state. You just have to, pure state is like inseparable wave function, which cannot be written as the, tensor product of two separated wave functions. So there are three layers hierarchy. Okay. So I hope things are clear. So I had made a tabular form. I mean, using notebook LM, I made this table. Okay, here we can have just a glimpse of what I was talking about. Local hidden variable model, Bell non-locality, it puts a stricter boundary. Okay, so some of the very not so, not so clearly pure quantum mechanical state, they may not be that, but still they can be eligible for communication, because that's what is practical. We cannot have absolutely pure states, shooting around for experiment. You will have mixed states. Okay, so this kind of a probabilistic distribution, if you can formulate to explain that, then the system, the system is not appropriate for communication. You have to be unable to model the system in this form. Similarly, in local hidden state model, which concerns one of the receiver state can be modeled as a local quantum state. Okay. So this is the overall picture that we have to have an inequality sort of thing, which has to be violated by a system, described by some wave function or a density matrix. Density matrix in general will quantify a mixed state. Okay. So this was the first lead. So here the idea is, and this makes use of the principle of Heisenberg uncertainty principle. Okay. So Alice is trying to infer based on her measurement, is trying to infer the results of Bob, and we calculate the variance of that say XP. I mean, this can be generalized this XP and PB, but you can generalize for any operator. If and XB is the position, I mean, in this case, position of Bob, I mean, position of the particle that Bob has. So this term is the expectation value of the square of the difference of the actual measured value of X by Bob minus the estimated value of the position of XB, position XB, on the basis of the measurement that Alice made. We just have represented by this. So this expected this kind of a, so this is called the inferred variance of XB. Similarly, inferred variance of PB. And XB and PB, they obey Heisenberg uncertainty principle. So from that, I will not go into the mathematical detail. You can refer to this paper by Reed, which was published in 1989. Great detail of mathematical derivations, which will land us in this inequality. Inferred, the square inferred variance of XP multiplied by squared inferred variance of PB has to be greater than equal to 1. Equality by assuming a local hidden state model. So if this inequality is violated, this will imply that the quantum system, whatever system we were considering, steering exists. I mean, there is some non-local effect is there. Okay. So this equation has to be one. Okay. So it is it's quite interesting actually. So many insights are yet to be, grasped from my personal point of view. But you see, a question might arise. Actually, this question I actually asked myself while preparing for this talk. So this is some kind of an inequality which is based in Heisenberg uncertainty principle. And quantum mechanical systems are supposed to obey Heisenberg uncertainty principle, right? But here I'm saying that if this equation is if this inequality is violated, then steering, I mean, some quantumness is there. We are saying. So the answer is we are establishing non-locality here based on a local hidden state which would obey Heisenberg uncertainty principle. All those things. Based on that, this inequality we have derived. If there is some sense of non-locality, then this kind of an inequality will be violated. So this inequality comes from the idea that the particle with Bob has some local definite quantum state, and it obeys its own Heisenberg uncertainty principle. Based on that, we derived this inequality, and that that basically implies that there is no non-local correlation. So if this gets violated, then there is non-locality. Okay, so that's the idea. Now, I'll try to wrap up within 2-3 minutes. So we can improve this this inequality, which tests. I mean, if some quantum system violates this inequality, it will be eligible for some secure communication. That's the idea. But we know that there are even stricter uncertainty relations. Okay, and the one of the most popular stricter uncertainty relation is the Schrodinger-Robertson uncertainty relation, SRUR, which actually takes into consideration many other terms, the covariance terms, the commutator terms, and you see if in this expression, if we substitute delta x and delta p or any canonical conjugate variables, these will reduce to zero, and this commutator will give you x and p commutator happens to be I into h, right? No, only iota, I guess, or I by h. Sorry, whatever. So this will reduce to h cross by 2, which will be the Heisenberg uncertainty principle involving position and momentum. Okay, so you substitute the commutator of x and p here, and these covariance terms. This is the anti-commutator, and these terms. These will go to zero. So basically, this stricter uncertainty relation works for any general operators which do not necessarily have to be canonical conjugate of each other. Okay. Okay. This was just a description of how covariance from a what does it exactly signify? Okay. So based on this uncertainty principle, Schrodinger-Robertson principle, you can also achieve or arrive at this kind of an inequality, which are all inferred variances, just like the inferred variances we described here. Similarly, inferred. So this is just this cannot be just a priori said to be very trivial. Just from this equation, you can just simply write this. So we have actually by using quite a lot of inequalities and probabilistic arguments, we have derived this inferred expression for the inferred variances of two operators x and y. And if some system, some quantum system described by some density matrix violates this inequality, it will be legitimate for secure communication. So, for example, we took the isotropic states in 2 dimension. D is the dimension here. So, means if D is 2, that means you have a qubit, 2 eigenstates. If D is 3, you have qubit, right? So, 3 eigenstates. So, you clearly see this is a mixed state represented by this density matrix, and using that state, we calculated we substituted all those values, expectation values, in this inequality. So using Heisenberg uncertainty principle, okay, we see that P, so basically this inequality reduces down to an inequality which basically P is greater than 0.61. Okay. But using this Schrodinger-Robertson uncertainty relation, we have a stricter bound, which is P is less than 0.56. Even a low, I mean, using the HUR, Heisenberg uncertainty principle, the claim was if P is less than 0.61, okay, then rho is steerable. But we have a stricter bound that if P is greater than 0.56, even then also it is steerable. Okay. So previously some state which lies here would be rejected by Heisenberg uncertainty principle based inferred variance relation. Okay. So this will in a way more accurately characterizes any mixed state, whether it's eligible to be used or not. So that's the basic idea, and some scope for future work for more number of dimensions in which the covariance terms can be written in matrix form, and we become more challenging. But so I think this is where I end my talk. Thank you, Professor. So,
Professor, I have one question.
oh,
Sorry for Professor. So this structure can be understand for a quantum sensing kind of purpose, in so that it's some kind of
yes, it can be implemented in any quantum. Quantum sensing means you mean to say some
probe.
some
Not
hardware
really not sensing,
some device which uses quantum
so
mechanical
some kind of
to sense,
detection
right?
of intelligence, so
Right.
not actually
Yes,
sensing.
it can be used.
It can be used, right?
We'll have to give it a thought how it may be implemented. So this is the basic structure, how to separate out eligible states from ineligible states.
Yeah, and another point is that you have mentioned that it will be interesting for the POVM measurement. Why you think so?
No, it can be extended to many. More than one operators. More. we just talked about 2 or 3 dimensions.
Okay.
It can be extended to more dimensions.
More dimensions. So in the higher dimension, we expect that there should be a positive impact. Right? We could expect.
Yes.
Okay. Okay. Thank you. Thank you. It was very
We'll have to be,
nice.
some of the questions also have to take some time to, uh, answer and, introspect.
Yes, yes. It's very nice and emerging topic. So we hope that you will share some thoughts on this. So I think Dr. Supriyo Roy have raised his hand, so you can
Oh,
ask a question.
Hello, Dr. Das. Am I audible?
Yes.
yes, sir. Yes. Yeah.
So, thanks for very nice talk. So, I have a simple question. So, if you can go back to your slide where you are explaining that SRUR equation, which is some sort of you have an extra term added to the
Okay.
Heisenberg's uncertainty principle.
This equation?
This one or some Schrodinger and SRU or something like that. I think.
Yeah. Based on this. Yeah. This one, perhaps you meant.
Yes. So you just said that if we have the second term to be 0, then we are
Yeah.
actually reaching to the Heisenberg's uncertainty principle, right?
Right.
So, so the second term, is it somewhat related to the degree of entanglement or something like that? Like which Heisenberg's uncertainty principle means, and then these term gives that additional physics that which actually incorporate the concept of entanglement. Is it something like that?
Uh, it's like
Or
two operators. Yes, two operators, which we have chosen. We chose operators like x and p, or angular momentum along two orthogonal axes, right?
okay, okay,
But if we choose any general, any two operators
hmm,
which do not have some sort of this canonical conjugate relationship and all, or orthogonality,
okay.
there these kind of terms will have to appear.
Oh, okay, okay. So it is in full coherence with the Heisenberg's uncertainty principle, right? So if the
Yes,
terms are conjugate, then the second term goes to 0.
right,
Okay, this is nothing, no addition. So it's naturally goes to 0 if we choose the variable such a way, in a
right.
certain fashion, right? Okay, okay,
Yes, I think so. Yeah.
okay. Thanks.
Okay, thank you.